Okay? Now, Py, okay, it's partial with respect to y, is what? It's the second partial of v with respect to x and y, because p is a partial of v with respect to x, right? Okay? Now, what's qx? Well, q is partial v with respect to y, right? So it's the x derivative of that. Well, these derivatives are the same. So Py equals Qx.
Are they always the same?
They have to be. If f is a gradient, then P has to be this and Q has to be this. And you know from partial derivatives that the order in which you take the partials makes no difference. And if you don't know that, you need to practice partials a lot more. And go back and review your homework, okay? If you didn't lock that in, because it's kind of striking when you first see it. Now, if you're smart enough, when you first see it, you say, oh, well, that's obvious. And it doesn't strike you, and then you forget it. So being smart can be a handicap. And that's probably why you aren't necessarily familiar with this property. If you aren't, because you're kind of like a little dubious. But yeah, it's property, it's easy to prove. Okay? So, we have this, right? This is the test. For conservative field. Okay? Now when you get to 3 dimensions, the test gets a little more extensive, but that's where you use the curve. Okay? And we'll deal with that when we get to it. Right now, that's sufficient to get you started. Very easy test. So what we know about conservative fields is the fields of this nature. Okay? If we know f, we do these integrals and figure out what v is. If we know v, we can do its gradient and find f. And if we want to know whether it's even worth doing these integrals, we test to see if it's conservative, because if it isn't, it's not going to work out. Okay? That's it in a nutshell.